you guys want to look at that or not. There. Jacquard's loom. Yeah, as I said, the loom, they kind of like they used to have these pianos that they called player pianos. And they also had these things which were music boxes. You'd open the lid and I think it would spin around and make a noise. And so basically it was just little points that would hit on different things and make a different noise. The same kind of idea, right? So with the piano, you'd put a card in and it would play the piano without anybody sitting at it. And that's the same here. You'd put a card in, and depending on where the hole was in the card, it would set up the weaving of the fabric. And so Charles Babbage, he made this difference engine. Again, it's just a machine that does mathematics. And here's some pictures of it. And so you can see it's quite a complicated machine. Later during World War II, which is during the 1940s, Alan Turing was able to use machines that had these ideas in them, but a bit more complicated, and uses electronics. I'm seeing people's eyes are starting to fade a bit. You know, I won't go for a full 2 hours. Don't worry about it. I can see that we're not going to get there. So I'll give me a minute, and we'll sort of we'll finish up on this, I guess. Ada Lovelace, or Ada. There's actually a programming language called Ada, or yeah, I call it Ada. So she was one of the first people to actually write a programming language. That's not what she called it. Ada is a programming language that somebody else developed during the 1970s, 80s. It's kind of like, there was another programming language called Pascal. Actually, it's like one of the first programming languages that I ever learned. So named after Blaise Pascal. But she was able to sort of actually look at, funny enough, Pascal's work and come up with some notes on how to do that. And she created a programming language. Now, Hollerith is interesting because it shows I think, the importance of sort of big economies driving these types of things. So the point there was the United States have a census, and they were a high immigration country. They still are, but back in the 19th century, they're a very high immigration country. And so they needed to know how many people were there and where they were. And so they did a census for that. Now, that's important for a lot of reasons. You want to know where they are, where they're going, so they can build things, but also for their politics, because they would assign different Congress areas depending on how many people were there. And so if you got a whole lot of people move into a new area, you might need to have a new congressional area, a new political representative. So they had to know all that stuff, and they would do these things, and it would take them like 10 years between each census. And then it would take 10 years to add up all the numbers. And anyways, Hollerith sort of maybe thinking about that loom thing. He said, well, you know, I got this idea. Maybe we can use these punch cards as a way of recording the information that's coming in from the census. And so he came up with that, and he had this machine, which he called the Hollerith machine, which people had to, you had a special kind of like a typewriter, which would enter the information onto a card, and then the cards could be read and collated, and you could do a much quicker sort of totaling of the number of people. And so that's what this is trying to show. This lady there is entering information, which then is to punch a card. And so we get these cards like that. And then the card could be read by a machine, and depending on where the hole is in the card, we could get that information. Now, something kind of like that is still being used in some testing places. People would hand out tests, and you'd have to sort of circle, you know, to have a grid. And you'd use a graphite pencil, and you just put your thing, and then very quickly you could get the results out of that. Now, we've gone away from that now, haven't we? Because now we got D2L and lockdown browser. We can do it all online, right? Save paper and graphite pencils. Anyway, so the thing that evolved out of that was these cards that used to be punched, and then they had them that they used to use pencil on them. When I started computing, my first degree was in chemistry, actually, but I still had to do a computer course. Science course, we had to do a computing course. It was actually part of the math course. Yeah, so the first computer program I ever did was not using not using these. We had one where we just used to use a pencil and put the numbers in that way. And then you'd take your deck of cards to the computer machine, which is a room, right? And you'd put the cards in there and it would read the cards, and then an hour later you'd get the result. Those were the days. That was to write a little program with like 20 lines in it to do the average of 10 numbers. Yeah. Okay. So having said that, this big thing there, that all one computer. So back in the 40s, they had these huge computers. Now they would be using those vacuum tubes that I mentioned that take a bit of time to heat up, and they also break. So it was really a hassle working with computers in those days. They use a lot of electricity. Like one computer would use electricity like a whole little town or city. Yeah. And they didn't think they needed many computers, right? So look at that little note at the bottom there. Only 6 electronic digital computers would be required to satisfy the computing needs in the United States. That's what he thought. So they were so expensive. They took up so much space. And they used so much. And, you know, who needs this computer, right? We only need it to do the census. But didn't take long for people to start seeing that you could use computers in things like banks, and governments could use them, you know. But yeah. All right. So I was telling you about the TV warming up, and, you know, the light coming. TV used to take a while to warm up. In the back of the TV were these things. These are vacuum tubes. They call them vacuum tube because, you know, the bulb is sealed. There's no air in there. Before they seal the bulb off, they extract the air from it. That's why sometimes some of our light bulbs are like that, I think. And if they break, they fall, right? Because they implode, right? But these were a little bit harder than that. They're not going to implode because they're a bit more sturdy glass. But they do burn out, kind of like a fuse. So you'd have to go around the machine and replace them all, right? Whereas our integrated circuits don't. So each one of these is like one gateway. And in an integrated circuit, a transistor, which is then implemented into an integrated circuit. Integrated circuits came after transistors, but in a transistor, you got one circuit. But then an integrated circuit, you can have millions, billions of circuits. So you can replace millions of billions of these into a single chip, because integrated circuits could go on a chip. And so that's why our computers are so powerful, right? I mean, this is way, way more powerful than anything that you're seeing here, right? Our computers are so, because of this miniaturization, that really made computing work for us. Alan Turing was an interesting guy in the 1940s, a bit of a hero amongst the British, because the German military, but particularly their navy, the Kriegsmarine, they had special codes. And so they had a machine that produced these codes, and the machine was called the Enigma Machine. And they actually found some of these Enigma machines. But the thing is, the Germans were sending codes, you know, and the codes would say when they had U-boats, when the U-boats, where the U-boats were, and because U-boats were really hard to find in those days, and they were sinking a lot of the British Navy material, as Britain was isolated, and it was getting most of its material from the United States and Canada, which is coming over the North Atlantic. And so the Germans, their strategy was to just sink as much of that stuff as possible. And so they'd put their U-boats out there to do that. And they'd have their codes where the military in Germany would send instructions to the U-boats, and they'd send it back, and it was coded, and nobody knew what it was, right? And so what Alan Turing did is he was able to take one of these computers that was being developed kind of experimentally by the people, they called them at Bletchley Park, and he was able to, by brute force, that's any of you guys going to do data security? Computer security. Anybody doing that? All right. Well, if you were, you'd be interested. So if you're not, I will go over that quickly. But a brute force attack, what it is you just sort of compute every possibility of a bunch of different ways of doing things, and you can break somebody's cipher if it's not too complicated. And so he was able to do that. They were able to break the German cipher. And so for a couple of years in the war, the British actually knew what the Germans were doing, but the Germans didn't know that the British knew that they were doing it. And that was a big problem for the Germans. They lost a lot of submarines, but it was good for the British, I suppose. Now after the war, so Alan Turing, so other things about him, such an interesting guy, so sad. The guy, well, some things you don't want to talk about. Anyways, you can read about it. Let's just say he didn't live to be old like me. And he had a bit of a rough life, but he's sort of a genius. But I guess the point that I'm making about that is people are just so complex, right? You can't just look at somebody and say, this guy's like that. He's just lots of things. And some of the things you might not like about him, right? I mean, there's some things about Alan Turing you think, that guy's creepy, man. But he's a genius. You know what I'm saying? So anyways, if you're interested, you could look at that, find out about it. A lot of people thought he was creepy, and he had a kind of a sad life because of that. And it didn't last that long. So the Eniac. So now we're going in our history back to the United States after the war. They're building these large computers, and again, they didn't think they'd need too many of them, but they were using them for, well, as I said, they'd use it again after the war for the census, and you can see that it was kind of big, 42 times 9 feet tall times, so 42 times 2 foot wide, so feet. So 9 feet is like 3 meters. And 2 feet is like 600 millimeters, 60 centimeters. So 42 times 600 centimeters, right? 600 millimeters, kind of big. Use a lot of power. Anyways, and so I thought that was kind of cool. So these were the machines that they were using in the 1940s, 50s, up until the 1960s. Now, you might remember, you won't remember, but you might have read somewhere history of the 1960s. What was the thing that was really sort of a big thing was the Cold War. And so the Cold War was the dominant nations. There was the United States on one side and the Soviet Union on the other side. And they both were very interested in space. And part of the reason they were very interested in space, go back to World War II, what the German engineers were able to do from about 1943 on is they were able to produce these rockets that would fly from Germany into England and sort of blow up in England. And so the person who led that development was a guy by the name of Wernher von Braun. Interesting enough, Wernher von Braun, at the end of World War II, moved to the United States. How'd that happen? Anyways, if you get interested in like the first man on the moon, when you look at any movies about the first man on the moon, you'll see Wernher von Braun there, standing beside President Nixon, sort of congratulating because it was his program, right? So Wernher von Braun. Now, Wernher von Braun had some ideas, like his rockets use kerosene, which is the same thing that jet engines use. And so, that's the rockets that they were using. But there were some, another interesting thing, right? Wernher von Braun became teammates with a scientist in the United States. I can't remember his name, but he was Jewish. And Wernher von Braun was a member of the National Socialist Party, also known as Nazis. They weren't very fond of Jewish people, but they kind of got to work together, which is kind of interesting. And anyways, the other scientists, they like to do hydrogen, which is kind of a dangerous way of going in some ways, you might think, but hydrogen's a lot lighter than kerosene, but harder to deal with. But in fact, that's what they ended up using in their space program. So I mentioned that the Soviets also had a space program, and they were ahead. Go figure. Until about 1967, they were ahead in the space race. It looked like the Soviets would get to the moon. That seemed to be the objective. to get to the moon. It looked like they would get there first because they had the better rockets, and they had it seemed to have gone better for them. They were the first ones to put a capsule into orbit. But I don't know if you're interested in this or not. I don't know. Anyways, long story short, there's no long story short with me. It's always just long story long, right? But what happened was that they had to get this spaceship to the moon, and it takes a lot of energy to get a spaceship to the moon, right? You don't want to be hauling around one of those computers like we saw there. That's many, many tons. And so they spent a lot of money on what can we do to make computers smaller. And so actually the transistor and the integrated circuit, you could say, were developed by Intel, and they were getting their money from the United States government, who wanted to do space. And they wanted something that they could put into a computer, into a spaceship that wouldn't, wouldn't take up too much space and weigh too much. And so I don't know what you think of the space program, but I think without it, we'd probably still be waiting for phones, for iPhones, you know what I mean? Yeah, so we got to be, that's where those things come from. So there's some more stuff on that. Germany, everybody's got their own sort of heroes on that. I think I'm going to stop about now, because this is where we actually start getting into computing. So there you go. Is that enough history? Is that enough? I mean, now I hate to say this, but there will actually be questions on the quizzes and maybe even a test on history. Really, sorry. And they're multiple choice, so there's only one answer, so you have to get it right. So sorry. So I do look at it. This is where we start getting into some real interesting stuff. Again, the Germans, they keep showing up, right? There's this guy, and his name is von Neumann. Von Neumann. There he is there, von Neumann. Is that him? No, that's, yeah, there he is, John von Neumann. And he was able to come up with this concept here, which is, you know what? The best way for us to do computing is what we'll do is we'll take some input and we'll put it into a processor. The processor will process the input. The processor will be made up of other subcomponents. So we'll have a control unit. What the control unit does is that actually controls what step happens next. Then we'll have an arithmetic logic unit, which is going to do all the calculations. The arithmetic logic unit, the most important thing that it does is it compares things. Is this bigger than that? Is this smaller than that? And so we can use it for sorting, but we can also use it for adding and subtracting and multiplying and division. And then we have a memory unit. So we've got a little bit of storage in the CPU, got a bit of storage or associated with the CPU. So what we've got is we've got input, we got processing, we got storage, and we got output. And so that, I don't know, when was that? 1950s, 60s? That was 1940s. Okay. That was the schema developed by von Neumann, and that's what we still use now. I mean, that's how we understand what we're doing in computing. Came to us from von Neumann. That's all of our machines are built on this sort of idea. And I'm going to leave it at that because I think this is a new idea. It's historical, but it's kind of important in the actual sort of conceptual part of it. So I'm going to leave it at that. And I think that's a good place to stop. I did say that I won't talk for 2 hours, so I'm going to just leave it at that.